Part 3, the binomial theorem. Study the following expansion of x plus y to the n. Okay, so this is a binomial. The x would be the first chunk of the binomial, the y would be the second chunk, and n, of course, is the exponent. So if we have x plus y to the 0, anything to the 0 equals 1. X plus y to the 1 equals x plus y. Okay, and then x plus y squared, okay, so that would be x squared, right? The last one would be y squared, and then we have that middle term, the 2 times x times y. So we've done these, the first three, quite a lot, not always together, but we've done them before. Now, if we expand x plus y cubed, okay, that's this array here, x cubed plus 3x squared y plus 3x y squared plus y cubed. Okay, x plus y to the 4th is all of that, x plus y to the 5th is all of that. Okay, and there's just patterns that I want you guys to recognize. So I'm just going to draw some lines here. Okay, so this is called row 1. This is row 2, row 3, row 4, row 5, and then row 6. Okay, awesome. The exponent here, so this is the row, this is the exponent. Okay, and then we also want the number of terms. Okay, so the exponent here was 0. The exponent in this one was 1. The exponent in this one is 2. The exponent in that one's 3. The exponent is 4, and then 5. It just goes up. Okay, so the number of terms, so 1 just counts as one term. X plus y counts as 2 terms. Okay, x squared, 2xy, and y squared, that's 3 terms. So 4 terms, 5 terms, and 6 terms. Okay, so there's a few things that I want you guys to recognize. Okay, so there are always one more term than the exponent, so n plus 1, right? The exponent here was 0, we had 1 term. The exponent was 1, and we had 2 terms. The exponent was 2, we had 3 terms. The exponent was 3, we had 4 terms. Okay, so the row number and the number of terms is the same, which is always 1 higher than the exponent. Okay, so tell you what, the sum of the exponents on the x and y in each term is what? Okay, so the first one doesn't have any exponents, so no exponents there, so 0. Okay, the x has an exponent of 1, the y has an exponent of 1. Okay, so the sum in each term is just 1. Okay, now this guy has x squared. These are both 1, so 1 plus 1 is 2. And this guy has y squared. So the sum of the exponents in each term is always that. Look, this guy's 3, that one's 3. Okay, 2 plus 1 is 3, 1 plus 2 is 3, and 3. So the sum of the exponents in each of the x and y in each term is always just whatever that original exponent was. Okay? If we have a look at just the exponents x, now I'll erase some of these just so you can see better. Okay, if we look at the exponents, let's say the last one, see it goes x to the 5, x to the 4, x to the 3, x to the 2, x to the 1, and then no x's. Okay, so the exponents on x decrease term by term from n up to 0. So it starts at whatever the exponent is. So in x plus y to the 5th, we start at x to the 5th and go all the way down to x to the 0. Okay? The exponents of y, on the other hand, the exponents of y, they start at 0 and they go up one at a time. So 0, 1, 2, 3, 4, and then finish off with x to the 5th. So the exponents of y increase one at a time from 0 up to n. Okay, and then the coefficients of this expansion. So if we just look at the coefficients now, so look at this. The coefficients are, so that's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. Okay, it's a symmetrical pattern. Okay, so it's a symmetrical pattern of coefficients. It's kind of neat. Okay, now remember, there's some patterns here. So how many terms would there be in the expansion of 2x plus 3 to the 8th? Okay, so if we're going to have a to the 8th, remember, so the exponent, okay, so that's these numbers, the exponent, okay, is 8. Now the number of terms and the row number is always one more than that exponent. So here there's going to be 9 terms, and we're going to be in the 9th row of this particular pattern. So 9th row, 9 terms, the exponent is 8. Okay, so if there's 18 terms in this particular expansion, what's the value of n? Okay, so if there's 18 terms, that means that exponent must be 17. So 3x plus 2y to the 17. Okay, well that means if the exponent is 17, so that means 17 has to equal 2n plus 5. Okay, so minus 5, so 12 equals 2n. So n equals 6. Okay, so this little pattern here just helps us expand any binomial, and we'll get to that here in a minute. We're just kind of learning some basic patterns right now. Okay. All right, the coefficients in the expansion of x plus y to the n can be put into a triangular array known as Pascal's triangle. Okay, named after Blaise Pascal, who developed applications on this triangle in the 17th century. Pascal was not the first person to discover this triangular array of numbers. It was known in India, Persia, and China centuries before. The Chinese call it Yang Hu's triangle in honor of Yang Hu, who lived from 1238 to 1298. Okay, so even though we call it Pascal's triangle, he just developed some of the applications. He didn't actually develop the triangle itself. Okay, so these are all the coefficients we saw from the previous page. So just the coefficients. No x's, no y's, just the numbers out in front. Okay, called Pascal's triangle. And I need you to have a look at this for a second, and can you see the pattern? Okay, maybe that's enough time, maybe it isn't, but that's okay. You notice first that there's ones on all the outside edges. Okay, and then if you look at these parts, okay, 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. Okay, 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So how we get the successive numbers of Pascal's triangle is we just add the two terms, so there's always ones on the outside, okay, and we add the terms to get the next row. So 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5 is 15, and 1 plus 5 is 6. Okay, so we want to use this pattern to make the next 3 rows of Pascal's triangle. So that's the first one. The next one, okay, so ones are always on the edges. So 1 plus 6 is 7, 6 plus 15 is 21, 15 plus 20 is 35, 20 plus 15 is 35, 15 plus 6 is 21, 7 and 1. See, it's a symmetrical pattern. Okay, and then of course the last one that they wanted us to do, so 1, 8, 28, so 21 and 35. makes 56, 70, 56, 28, 8, and 1. Okay, so this is Pascal's triangle. Okay, and we can use Pascal's triangle to expand the following binomials. So if we want x plus y to the sixth, look what happens, or how can we do this? Okay, so remember the sixth, so this is the seventh row. Okay, and we didn't use the term Pascal's triangle last bit, but it's the seventh row of Pascal's triangle, and there's 7 terms. Okay, so remember, this is the first row. Okay, row 1, row 2, row 3, row 4, row 5, row 6. Okay, so row 7 is this one. Okay, awesome. Now, also remember, so this is the one we want for this guy. Just so you can see it good. Okay, so these represent the 1, 6, 15, 20. Those represent the coefficients on the expansion. Remember, the x coordinates or the x values start high and go down one at a time to 0. The y coordinates start at 0 and go up one at a time. So the first one is going to be simply x to the 6th. Okay, and that makes sense because it's x to the 6th. Great. It's where all the middle terms that we get into trouble. So Pascal's triangle is great for that. So x to the 6th plus. Now the next one is going to be 6, okay, and then x to the 5, so the x's go down and the y's go up, y to the 1. Okay, the next one is going to be 15, x's go down, x to the 4th, y squared, okay, plus 20, x to the 3, y to the 3. Okay, now we're on the 15, so plus 15, x squared y to the 4th, plus 6 x y to the 5th, plus 1 y to the 6th. So that we can use Pascal's triangle to expand these binomials to whatever exponent we want. It's really quite brilliant. Okay, so let's try this next one, x plus y to the 8th. Okay, so that would be the 9th row of Pascal's triangle. So this was the 7th row. This is the 8th. So this is the 9th row. Okay, the exponent is 8. Okay, and then so we use that last row of coefficients. So the first one is going to be 1x to the 8th. Okay, then plus 8x to the 7th, y to the 1. Awesome, because the x's go down, the y's go up. Okay, so then plus 28 x to the 6th y squared plus 56 x to the 5 y to the 3 plus 70 x to the 4 y to the 4 plus 56 x to the 3 y to the 5 plus 28 x squared y to the 6th plus 8x y to the 7th plus 1y to the 8th. Wow, that's just enough room. That's crazy. Okay, anyway, so we can use this Pascal's triangle thing to expand our binomials. Awesome. Okay, so one of the most useful things about Pascal's is the connection between the triangles and the combinations. As it turns out, the entire triangle can be written with combinations instead of numbers. So 0 choose 0 is 1. 1 choose 0 is 1. 1 choose 1 is 1. 2 choose 0 is 1. 2 choose 1 is 2. 2 choose 2 is 1. Okay, so we can use this whole array using combinations. So that's why it fits into permutations and combinations, because that is going to be really important later on. Okay, so I've made a little chart over here, row, exponent, and number of terms. So let's just fill that out one more time because it's kind of a big deal. So in row 1, the exponent was 0. Remember, that was x plus y to the 0. And the number of terms was 1. Okay, in row 2, it was x plus y to the 1, x plus y to the 1. So the exponent is 1, and the number of terms again was 2. So notice the rows always go up, 3, 4, 5, 6, 7. Okay, the exponent is always 1 behind the row. So 2, 3, 4, 5, 6. Okay, so this particular expansion, this row would be x plus y to the 6th. Okay, and then of course the number of terms is always 1 higher than the exponent, or equal to the row number. 5, 6, 7. Okay, so we're going to just very quickly fill out the rest of this grid. So row number 1, 2, 3, 4, 5, 6. The number of terms is exactly the same. 4, 5, 6. Okay, the value of n, or what's the exponent, so that's always 1 behind. So 0, 1, 2, 3, 4, 5. Okay, now this next column, sum of the coefficients. So then that's just adding all the numbers together. So in the first one, just there's nothing to add, it's just 1, so 1. The next one, so 1 plus 1 is 2. In the third row, we have 1 plus 2 plus 1. Okay, that's 4. Okay, in the next one, we have, so I'm right here in case you're having trouble following. Okay, woo, right here, yay. Okay, so 1 plus 3 plus 3 plus 1, that's 8. Are you seeing a pattern yet? Let's do one more. 1 plus 4 is 5, plus 6 is 11, plus 4 is 15, plus another 1 is 16. Look at this, 1, 2, 4, 8, 16. I'll bet you the next one is 32. Okay, so 1 plus 5 is 6, plus 10 is 16, plus another 10 is 26, plus 5 is 31, plus 1 is 32. Hey, look at this. It makes a doubling pattern. Okay, and in general, the sum of those coefficients is 2 to whatever the exponent is, right? 5 to the 2 is 32. 4 to the 2 is 16. 3 to the, sorry, ugh. Wow, did I ever say that wrong? Okay, 2 to the 5th is 32. 2 to the 4th is 16. 2 to the 3rd is 8. 2 squared is 4. 2 to the 1 is 2. And 2 to the 0 is 1. Okay, so let's use that and do these next few examples. So what is the sum of the numbers in the 12th row of Pascal's triangle? Okay, well, the 12th row, remember the rows are always one ahead of the exponent. So that means that the exponent, n, is 11. So the sum of the coefficients would be 2 to the 11. Okay, and that works out to 2,048. So what is the sum of the coefficients in the expansion x plus y to the 9? Well, that's just 2 to the 9. So that's 512. Okay, great. So what is the sum of these? So 10 choose 0. Okay, so this one here, starting with the 10, see, that's a little bit tricky. Let's just go back to where the combinations was. Oh, that's up here, sorry. Okay, so the combinations. So in the first row, we had 0 choose 0. In the second row, we had 1 choose 0. Third row, we had 2 choose 0. Fourth, 3 choose 0. Fifth, 4 choose 0. In the sixth row, we had 5 choose 0. In the seventh row, we had 6 choose 0. Okay, so 10 choosing 0, okay, that would be the 11th row. 11th row again. Okay, so if that's the 11th row of Pascal's triangle, okay, so then we're going to end up with the exponent being 10, so 2 to the 10 which is 1024. Okay, so we had to do a little bit of maneuvering on that one. Okay, not a big deal. Okay, and then, so this is the same thing, but look at this. 10 choose 0 plus 10 choose 1 plus 10 choose 2, all the way up. Oh, we stop at 10 choose 9. So we are missing that very last edge of the 11th row. Okay, so if we're missing that last edge, remember, it's always 1s on the outside edges. 1, 1, 1, 1. Okay, so there's always, so really, this is 2 to the 10th, but we subtract the 1 from the edge, so this is going to be 1024 minus 1, which is 1023. Okay, so again, just some neat patterns. Okay, while the material on the last few pages was interesting, the real contribution of Pascal and his triangle was to the expanding of a binomial, okay, called the binomial theorem. If the exponents are small, we could just expand them by hand. The binomial theorem is far too messy to expand x plus 5 to squared, or even, you might even go x plus 5 to the 6th. You might even be able to do that by writing out the first 7 rows of Pascal's triangle and expand it that way. However, the binomial theorem is a formula that allows anyone to expand any binomial expression one term at a time. So then it's expanding something like x plus 5 to the 17. It would take a long time, but it's very, very doable. Okay. Also, often it is not the entire expansion that's important, rather just one single term. The binomial theorem is really great for this. Okay, so the binomial theorem, which is on your formula sheet, and it says, in the expansion of x plus y to the n, the general term is t to the k plus 1 is n choose k, then x to the n minus k, y to the k, where t is the term position, so the first term, second term, third term, fourth term. Okay, n is the exponent, x is the first part of the binomial, and y is the second part of the binomial. Okay, so we're just going to practice this. I know this is brand new, so we'll go slow. So what is the third term in that expansion? X plus y to the 5th. Okay, so the third term, remember back from Math 20, we would say T3 for the third term in an arithmetic or geometric sequence. Okay, so T3. Perfect. Well, that's not how the formula is written, though. The formula is written as TK plus 1. So if K plus 1 has to be 3, what's K? Well, how I do this, guys, is I like to do this. So I'll write T3 and then I'll put K as 2 underneath. Okay, it's a really handy thing to do. Okay, hopefully that makes sense because it's just the way the formula is written. Okay, so I want the third term, so K is 2. So this is going to equal n. So in this case, n is the exponent, so 5. Choose K. Well, that's why we write the K down here. So it's 5 choose 2. Great. So 5 choose 2. And then we have the first chunk, so the A. Okay, and then that is raised to the exponent n minus K. So 5 minus 2. So 5 minus 2, which of course is 3. And then we have the B, the second part of the binomial, just to the K. So really, we type this into our calculator. 5 choose 2 is 10. A to the 3, B squared. Now look, if these were x's and y's, this would be 10x cubed y squared. So I just want to go back. So third term of x plus y to the 5th. Okay, so we want the third term of x plus y to the 5th. So we have x plus y to the 5th, and we want the third term. Look at this, guys. 10x cubed y squared. So our little example there was just a's and b's, but that's the third term. And I didn't have to write out Pascal's triangle. I didn't have to to expand it out longhand, it just figured out that term. Awesome. Okay. Now, let's try these next few. So the fourth term in this expansion, so I want T4. So remember, the formula is written as TK plus 1, so that means that K equals 3. Okay, so that's going to be N choose K. So N is 6. That comes from the exponent, right? So N choose K. K was 3. Okay, then the first chunk, so the first chunk of this is 4B. So 4B to the, now it's always N minus K, so it's the 6 minus 3. So 6 minus 3 is just 3. Now you're allowed to do that in your head because you can. You're in Math 30-1. You're a smart person or smart people. Okay, so N minus K is 3. Okay, and then the second chunk is negative 5. Okay, just to the K, so that's also to the 3. Okay, and then we just simplify or all that out. So 6 choose 3. When you type that into your calculator, it's 20. Now remember, a cubed goes to both of those pieces, so that's going to be 4 cubed B cubed. Okay, and then negative 5 cubed is negative 125. Okay, and so really when you type in 20 times 4 cubed, which 4 cubed is 64, so 20 times 64 times negative 125, that is negative 160,000 B to the fourths. B to the fourths. Funny. B cubed. B cubed. Okay. Right. B cubed. Okay. Awesome. Now, the middle term of this guy, 3x minus 2 to the 8th. Okay. This is where all that preamble stuff comes in really handy, because if the exponent is 8, we know that there's 9 terms. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And the middle term is that guy. So that's T5. So I'm looking for the fifth term. So K equals 4. Okay, great. So that is going to be the exponent. So 8 choose 4. Then the first chunk, 3x to the 8 minus 4, which is just 4. And then the second chunk, so the negative 2 to the k, which again is just 4. And now we just expand that out. So 8 choose 4 is 70. Okay, then we have 3x to the fourth, so that is times 81 x to the fourth, right? 3 to the fourth is 81, x to the fourth is just x to the fourth. And then negative 2 to the fourth is positive 16. If you're going to type that into your calculator, make sure you put the brackets on. If you don't, your calculator will tell you negative 16 and you'll get it wrong. Okay, so brackets for the negatives. Okay, and then you multiply all the coefficients or all the numbers, and you get 90,720 x to the fourth. So this is so much better than expanding these binomials out by hand. Like, how would you expand that by hand? It's next to impossible. So you could do it, but it would take pages and pages of work and time and just, yeah, this is so much better. Okay. So we have a few more examples and then we are done. Okay. So number 3, in the expansion of a squared minus 1 over a all to the fifth, which term in simplified form contains the variable a to the fourth? Determine the coefficient of this term. Whew. Okay, that's a loaded question, but that's all right. We're going to figure this out. The first thing we have to notice is, look, there are a's in the first chunk and then there's a's in the second chunk. And the a's in the first chunk are in the numerator, the a's in the second chunk are in the denominator. This is where using blanks is really, really helpful. So tell you what, it's all to the fifth, so that means there's 6 terms here. We're in the 6th row of Pascal's triangle. There's 6 terms and the exponent is 5. So 1, 2, 3, 4, 5, 6. Okay, awesome. 6 terms. Now, this is where all that preamble stuff gets to be important. So hopefully you were paying attention. If you weren't, we'll just try and follow along now. Okay, so this first exponent here is going to be all the first term, so a squared to the 5th. So a squared to the 5th, well, of course, that simplifies to a to the 10th. Okay, so tell you what, we'll do that later. The next one, remember the exponents go down one at a time. So that's going to be a squared to the 4th, a squared cubed, a squared squared, a squared to the 1, and then a squared to the 0. Okay, so I'm just going to write that out again. 1, 2, 3, 4, 5, 6. So a squared to the 5th is a to the 10th. A squared to the 4th is a to the 8th. Remember, you multiply exponents. So a to the 6th, a to the 4, a squared, and then a to the 0. So look what happens. It was an a squared. So when we started off then at a to the 10th and then went down by 2's. That is a pattern that's going to hold for whenever we have stuff like this. Now, the bottom, because this a is now in the denominator, our blanks can behave like fractions. So we did the numerators, but now let's look at the denominators. Okay, so the first exponent on the second chunk, remember the second chunk starts at 0 and goes up. So this is going to be a to the 0. This next one is going to be a to the 1. The next one's going to be a squared. The next one's going to be a cubed. Now remember, these are on the bottom. That's why I'm writing them on below the line. Okay, the next one's going to be a to the 4th. And the last one is going to be a to the 5th. Great, right? The exponents start low, start at 0, and go up one at a time. The exponents just happen to be on the bottom of the fraction, though. Okay, so let's write them over here, too. So a to the 0, a to the 1, a to the 2, a to the 3, a to the 4, a to the 5. Now, the whole point of this, everyone, is to figure out which term number. Because if I know what term number, then I could just use Pascal's triangle. The thing is, we don't know which term has a to the 4th in it. So that's why we do this, to figure it out. So look, we have a's on the top and a's on the bottom, and they're going to cancel. So, and remember, when we have exponents like this, the exponents subtract. So 10 minus 0 is 10. So the first one is a to the 10th. The second one, a to the 8th minus 1, so that's going to be a to the 7th. 6, 2, oh look, that's a to the 4th. Bing, 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 bing. Hey, that's the guy we want. So this tells us that we want the third term, right? It said which is a to the 4th. Then the next one would have been just a. So had the question said which in simplified form contains the variable a, it would have been the 4th term. This next one is going to be a to the negative 2. And the last one is going to be a to the negative 5. So I could have asked any of those things. This question just asked a to the 4th. So that's this guy. So it's the third term. So k equals 2. And now we go, okay, so the exponent was 5. So 5, choose 2. Then the first chunk, which was a squared. So a squared to the 5 minus 2, which is 3. And then the second chunk, which is negative 1 over a, to the k, which is just 2. Awesome. So 5 choose 2. That is 10. Then a squared to the third is a to the 6th. Okay, negative 1 squared is just 1, positive 1. And then a squared is, well, just a squared on the bottom. So this whole term works out to 10 a to the 6th over a squared. So that's going to cancel and make 10 a to the 4th. Great. So it has the a to the 4th in it. And we just want the coefficient. So the coefficient is just 10. Wow, that was intense. Okay, the example on the next page has another one of these just so we can practice, because those are tricky. Okay, and then so we do number 4 first. So one term in the expansion of this is 84x to the 5th. Okay, determine the numerical value of a if a is bigger than 0. Okay, sure. So this is going to be 8 terms. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, you don't have to draw all 8 blanks. I just find that it's really helpful. Again, very visual. Okay, so it works. Now the first guy, like again, we're aiming for the term number. As soon as we know the term number, then we can use Pascal's triangle. How we do that is we look at this part. We know it's x to the 5th. The first term is going to be x to the 7th, and it goes down one at a time. So x to the 6th, x to the 5th, x to the 4th. Hey, wait a sec. I know that my term has x to the 5th in it, so this is the guy. That's the term I want. So that's the third term, which means that k equals 2. So once I have that term number, then I stop with the blanks and I go to Pascal's triangle. Or the binomial theorem, pardon me. Okay, so T3, the third term, k equals 2. So that is going to be the 5, choose 2, right? No, sorry, looking at the wrong exponent. Okay, the exponent is 7, so it's 7, choose 2. Okay, the first chunk is x, so x, and then the exponent on that is 7 minus 2, which is 5. Again, that's right on the formula sheet. Okay, and then the second chunk is a to the k, so that is squared. All right, so we know that this term is supposed to be 84x to the 5th. Okay, so now we can do some algebra. 7 choose 2, that just works out to 21. So 21x to the 5th a squared is supposed to be 84x to the 5th. Well, you can see there's an x to the 5th on both sides, so the x to the 5ths cancel. Nice. Okay, and then 21a squared equals 84. Divided by 21, divided by 21, so a squared equals 4. So a is plus or minus 2, right? Square root, square root. But look it up here. It said a is bigger than 0. So that means the negative 2 is extraneous. So then just a equals 2. Awesome. So that is how we do a question like that. Okay, and then last, number 5 here. So find the constant term in this expansion. So remember, a constant term has no variable. Okay, so basically it means that the variable is going to cancel off. Okay, awesome. Again, if we knew the term number, we could just go right from here and use the binomial theorem. Well, of course, we don't know the term number. That's why it's a challenge. Okay, so we have to find that term number. Okay, so the exponent is 8, which means that there's 9 terms. 1, 2, 3, 4, 6, 7, 8, 9. Awesome, 9 terms. Now, how we do this, remember there's a's on the top, on the numerator, there's a's in the denominator. So we use those blanks as fractions. Okay, so there's numerators and denominators. Okay, so the first one is going to be, now don't even bother with the 2 for this part. It's just the a's we're looking at. So it's going to be a to the 8th. Okay, and then next one's going to be a to the 7th, a to the 6th, a to the 5, a to the 4, a to the 3, a to the 2, a to the 1, a to the 0. Okay, now, if there was not a's on the bottom, the constant term is usually that last one. But of course, there are a's on the bottom. Okay, so this guy here, remember the pattern. Okay, this is a to the a cubed, so he's going to start at 0, a cubed to the 0. Well, guys, that's just a to the 0, or nothing, so a to the 0. Okay, a to the 0. Okay, the next one is going to be a cubed to the 1. To the 1, which is just a cubed. The next one's going to be a cubed squared, which is a to the 6th. So look, it goes 0, 3, 6. So a to the 6th, a to the 9th, a to the 12th. And that's an up by 3 pattern because of the cubed. Okay, if the 3 was on the first chunk, it would start high and go down by 3s. Okay, because it's on the second chunk, it starts at 0 and goes up by 3s. Anyways, we've already found out what we need. Look, a to the 6th divided by a to the 6th, that's a to the 0 or just 1. The a's cancel. Either way, a's cancel here. 1 cancel here. So this is the third term. So T3. Okay? It's just whatever blank that is, so T3. So if we're on the third term, that is K is 2. Okay? Awesome. So that equals, so the exponent, so 8, choose 2. Then we have the first chunk, 2a to the 8 minus 2, so it's a 6. Then the second chunk, which is negative 1 over a cubed, to the k, which is 2. Awesome. So now we figure out what those things are. 8 choose 2 is 28. Okay, 2 to the 6th is 64, so that's 64a to the 6th. Negative 1 squared is just 1. And then a cubed squared is a to the 6th on the bottom. Okay, so the a to the 6th is canceled. That's why this is the constant term. And then 28 times 64 times 1. Well, you don't have to times 1, but whatever. Okay, it is 1792. So that is the constant term of this expansion. There's no variables in it, so that's it. Okay. Oh, sorry. One last little bit. Okay. One final application of Pascal's triangle is in the area of pathway problems. We saw these earlier in the unit with permutations with repetitions. So the question was, how many paths can you follow from A to B in a 4x6 rectangular grid if you only move up or to the right? Okay, awesome. Okay, in part 1C, we solved this problem using permutations, so let's do that again. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 roads, 4 of which are vertical, 6 of which are horizontal. Okay, so that gave us 210 ways of doing this. Okay, awesome. Now, I want you guys to verify your results using Pascal's triangle. Now, you haven't learned this yet, so this is where I'm showing you. So we're starting at A, and it's important to recognize that Pascal's triangle has 1s on all the outside edges. Now, if you look at this, from A, I can go out this way. There is one way for me to get to that corner. There's only one way for me to get to that corner, too. Just I have to go straight there. There's one way for me to get to this corner, and there's one way for me to get to this corner. Okay? There's one way for me to get to this corner. One way, one way, one way, one way, and one way. Now look, to get to this corner right here, I can go this way, or I can go this way. So there's 2 ways to get to that corner. Okay? Here, I'll draw an orange for just a minute. And I'm not going to do this very long because this is drawn out. To get to this corner, I can go one way, 2 ways, or I can go up this way and 3 ways. So there's 3 ways to get to that corner. Hey, why would Pascal's triangle be like? So this corner plus this corner, 1 plus 2 equals that corner, the 3. So 3 plus 1 is 4, 4 plus 1 is 5. Okay, so I can use Pascal's triangle this way. So let's go the other way because the numbers are small. So 2 plus 1, okay, so that equals 3. Okay, I'm going to erase this line because if I put all those lines in, it gets really messy. So 3 plus 1 is 4. 4 plus 1 is 5. 5 plus 1 is 6. 6 plus 1 is 7. So there are 7 different ways for me to get to this corner. Okay, I think we've explained that part enough. So 3 plus 3 is 6. 4 plus 6 is 10. 5 plus 10 is 15. Okay, remember that's these two corners to get to that one. Okay? And what we do is we just keep doing this until we get up to B. So 6 plus 4 is 10. 10 plus 10 is 20. 20 plus 15 is 35. 10 plus 5 is 15. 15 plus 20 is 35. 35 and 35 is 70. 15 and 6 is 21. 35 and 21 is 56. 70 and 56 makes 126. 21 and 7 makes 28. 56 and 28 makes 84. And 126 and 84 makes 210 ways of getting there. Okay? So we can use the permutations with repetitions to do this. Now this is shorter, okay, for sure it is, okay, but this is just one application of Pascal's triangle. Okay, great. So it works, it makes sense, and let's try another one. So we did this triangle, or this array as well, way back then. Now the answer in part 1C, it was 1050. So just so you kind of know what we're aiming for. Now, we're starting at A, so we go 1, 1, 1, 1. Okay, so on the outside edges, they're all 1s. Okay, so 1 times 1 is 2. Okay, 2 times 1, or 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 1 is 5. 2 plus 1, 3. 3 plus 3 is 6. 10, 15. 4, 10, 20, 35. Okay, that's 5, 15, 35. And then so this corner is 70. So there's 70 ways to get to that corner. Now, the thing is, the mistake a lot of kids make is they just put 1s on this triangle now. Well, that's not true. Okay, because there's 70 ways to get to here. Okay, because you have 70 ways to get to this corner, and you don't have a choice to get to this next one. So 70, so that number just carries on from there. 70, 70, 70, so this one is 70, and this one is 70. There's no choice. You have to go through this corner, the first 70, to get to those other outside edges. Okay, so now 70 and 70 is 140. Okay, 140 and 70 is 210. Okay, 70 and 140 again is 210. 210 and 210 makes 420. Okay, 210 and 70 is 280. So 280 and 420 is 700. Okay, 70 and 280, so 350 goes there. So 350 and 700 makes 1050. So that was the answer that we got from section 1C, and it's just one more application of Pascal's triangle. Okay, so you can use the repetitions or the permutations with repetitions, or you can use Pascal's triangle. There are times, like a complete grid, like this example, like the last example. This one is easier to use permutations with repetitions. Okay, ones like this are about the same, but there are types of pathway problems where you just want to use Pascal's. Okay, so that is how you do that. Okay, key ideas here. Pascal's triangle has many patterns. Okay, for example, each row begins and ends with 1. Each number in the interior of any row is the sum of the two numbers to its left and right in the row above. Okay, you can use Pascal's triangle or combinations to determine coefficients in the expansion of x plus y to the n. Okay, you can use the binomial theorem to expand any binomial in that form, x plus y to the n, any binomial at all. It's awesome. Okay, and then you can determine any term in the expansion of x plus y to the n using that cool little formula that we developed and is on your formula sheet. Okay, so you guys need to practice these. It's section 11.3 in your textbook, starts on page 542. There's a bunch of questions here. Remember, you can do more than these, but you have to do at least those ones. Okay, the answers are in the back of your textbook, and please print out the workspace card so you can write all over these. Writing on this stuff is helpful. You might not have enough room, so you might have to use loose leaf as well, but that's not a big deal. Now, this is the end of Unit 2. So you have a formative assessment to do on the whole unit. You have a summative assignment for the whole unit, so that's the one for marks. And then you have a Unit 2 exam or Chapter 11 quiz, whatever you want to call it. But this is all of Unit 2, so you have some assessments coming up. So good luck on those, and feel free to watch the videos again. Whatever you need, ask your teacher, email me. We will make it work. It's a fun unit. It's a nice unit. There's some challenges in here, but just remember, read the question carefully, and this one is one of the better ones. Okay, talk to you later. Thanks.